Okay, so electrochemistry is all about the chemistry of electrons being moved from one point to another and rerouted through some kind of resistor to perform some work. We call those batteries or sections of batteries Voltaic cells. Volta was an Italian scientist who developed the concept of electrochemistry, and so the word volt for joules per coulomb is named after him. Now, so what we're going to look at in this section is how the electrons were rerouted, how they started, and then we'll get into the mathematics of it in the next section. So for this one right here, we take a look at number 35 on page 886. You'll see that you have this cathode reaction, which is the oxidation reaction is the cathode part of the battery. Now, this is what we call a wet cell, in which case we've separated the two sides from each other, connected by what we call an ionic bridge, and we'll talk about that in just a little bit. But the wiring goes from the metal, from the cathode, in this case it's magnesium, because it's part of this reaction. Magnesium yields magnesium 2 positive plus 2 electrons. So the magnesium metal then, the wires attached to that, and as the electrons are being peeled off of this to get the magnesium, the electrons then are sent in this direction towards the other side, which we call the anode, and that's the reduction reaction, which is Ni2 positive plus 2 electrons use nickel. Now this is an electrode called, it's the anode itself is the electrode for which the electrons are received, and the cathode is where the electrons are sent. And the ionic bridge, because the electrons are going in this direction, then the positive particles are going up through this bridge. If you don't have the bridge, this reaction will not run and no electricity will be created. So the ionic bridge allows a flow of positive particles to move over here to constantly supply this side of the reaction. Now, there's something called a Voltaic cell notation, which is a shorthand form describing what's going on. So as you see here, the magnesium is your electrode. That is, the electrode is mentioned first for the cathode and last for the anode, because that's the end particle. The magnesium, which flows over here, is mentioned second. So you have this double line here which separates the cathode from the anode. So the cathode always goes first, the anode goes second. I don't care where you put it up here. I generally like to put the cathode first because that's the side which the Voltaic cell notation starts. And it's on the cathode side. I also note that they're not asked to do the Voltaic cell notation for number 35. I'm just simply putting it in there so you can see where that comes from when we start requiring that particular notation. Next one on 37, which is the next page over. This is the overall reaction, so we have to find the oxidation and reduction reaction. The oxidation reaction, this is 0 to positive 2, so the zinc is being oxidized, the silver is being reduced from positive 1 to 0. Now, I did not balance the equation because it only asks, in the cell notation, they don't ask for a balanced reaction. It's balanced here. We could have put the 2's here if we wanted to, but I didn't want to get that confused when you start doing the Voltaic cell notation. The only numbers on there are the charges, but you won't have coefficients like you have up there. And then you draw your cell notation, cathode, where the zinc ions are, and the zinc metal is the cathode itself. The anode is the silver. We have the silver metal strip right there, in which the wire is attached from the cathode to the anode, so the electrons allow to flow. The Ionic Bridge is where the positive ions then are going to migrate in this direction right here. Usually, like when we do lab sport, it's a piece of paper soaked with potassium nitrate, so the potassium supplies the positive charges. The next one is the Voltaic cell notation. That's what VCN stands for. So you see the nickel here is a solid, so that tells you that that is the cathode or the electrode for the cathode side. The nickel 2 positive then is what is mixed in that whole cell. And then on the other side, the reduction side, the anode is the lead, and that's the last thing that's mentioned. And then the lead 2 positive is in solution with that. And that's all you have to show. What happens though if you don't have a metal in your reaction? This is an example of that. We have an overall, we want to write the overall cell reaction for this Voltaic cell notation. Sometimes you'll see a comma here or a comma here, or sometimes a line. But the point is, the beginning and ending points describe the metals that are being used as electrodes, as conductors of electricity, or receiving electricity and passing on to the solution. This is going up in oxidation number, which is we expect being the cathode. So this is the oxidation reaction. You notice there's no metal in that. This is only there to allow the transfer of electrons. It is not part of the reaction. Same thing over there. We have no metal there. We have ions that are aqueous. We have ions that are aqueous, but they're not pure metals. And even if you did have some mercury here, you couldn't have mercury as an electrode. You'd have to have something solid, and mercury obviously isn't that. But even so, in ionic form, you have to have a metal. And platinum is perfect as an electrode because it does not react with hardly anything at all. So Hg positive gives Hg2 positive with this electron. Over here, Fe3 positive plus that electron gives you Fe2 positive. You already have the same number of electrons on both sides, so they cancel out, and everything else then gets left over. And this is your overall cell reaction or equation for that. And that's pretty much it. It's not too bad. So your homework assignment or practice problems on pages 886, 887, those problems. Have fun.